Hello, everybody. My name is Masood Olia, and I'm a faculty in School of Engineering at Wentworth Institute of Technology. And I'm here with an example of a machine in the subject of statics, where in this case we have a pliers, example of a pliers, where we are trying to figure out if we apply a 240 Newton force to the handles, what would be the output force right here in this section? So another what force are we applying on these nuts or washers or whatever it is the jaws are holding here? Okay, so this is a very good example where we would see if this pliers is efficient. So in other words, if you're applying a 240 Newton, you're hoping that you get much larger force at the jaws. So we'll find out in a minute. So let me call this force, or what we are looking for, the output force, F out. So that would be right here in this section. So we could actually start by drawing the free body diagram of the handle and work our way toward the jaws, which actually wouldn't be a good idea. If you start drawing the free body diagram of the upper jaw, and you'll see that actually we need some information for the lower jaw. And because of the symmetry, whatever we have on the upper jaw, pretty much we have on the lower jaw. So let me try to draw the free body diagram of the upper jaw, and right below it, I draw the free body diagram of the lower jaw. I leave some room here so we can see the forces better. So this is just as best as I can do for the free body diagram of these two jaws here. So what are we trying to find? We are trying to find this output force here. So right now, let me just concentrate on the upper jaw. So that would be in that section AA that is shown by a dashed line. So that's the objective. So now we'll look at different points. So we see point B here, which is 15 millimeters, 10 millimeters away from where section AA is, right? And then we see point A here. Now I want to tell you something about point A. You see how some pliers, they're adjustable so you can move the jaws. So what this means here is that since this guy is free to move in the horizontal direction, then there is no reaction in the horizontal direction is developed, only a reaction in the vertical direction. So I assume that that direction is like that. We'll find out in a minute. So let's call that reaction AY. Okay. And what's happening at B? Well, B, the first thing we look at is that at B we have a pin. The pin is confined, so it cannot move in the X or in the Y. So we got two components of reaction. So look, guys, by applying the sum of the forces, or actually sum of the moment, by taking moment about B, we can find out what AY is going to be in terms of this F out. So what I'm going to do, I'm going to get all my unknowns for the time being on this upper jaw in terms of this output force. We know the output force is an unknown by itself, but this will allow us to eventually, when we move to the handles, determine based on that 240 applied here, determine what the F out is eventually. So I'm going to go ahead and do this. So I'm going to say, look, we have, let's go ahead and take moment about point B, say is equal to 0, right? And then clearly, if you take counterclockwise to be positive or any direction for that. So what's the moment of F out about B? So F out times that distance, which is 10 millimeters. No reason, no, you don't have to change the units. Keep it in millimeters as long as you're consistent. And look at the distance between A and B. That is 30 millimeters, right? So the moment of AY is going to go negative clockwise times 30. So what does that imply? AY is going to be 1/3 of F out. So I just found this one. Let me just put it here. All right. So this AY is 1/3 of our unknown F out. By the way, one thing you notice is that since there is no horizontal component of reaction at A, if you balance forces in the X, what does that imply? There's no other force except Bx here, so Bx has to be 0. So basically, there are no reactions developed in the X direction on any of these pins, actually. And by summing forces in the Y direction and try to balance forces in the Y direction, remember that I'm still working on the upper jaw. So if I have F out in that direction and then 1/3 of F out, By has to switch, right? And become 1/3 plus 4/3. So it becomes 1/3 plus 1, which becomes 4/3 F out going in this direction. So let me do this. Let me clean this up. I remove the Bx, right? And since Bx is 0, right? So I'll now put this By to be 4/3 of F out. So that's all we get for the free body diagram of the upper jaw. Let's now do the same thing for the lower jaw. So you see in the lower jaw, we do have this same F out, right? So that's the force actually that washer exerts on the upper jaw here or on the lower jaw below it. Okay. Then we got what? Point E, which is just like point B here, right? And since this direction, as you can see, this should be then 4/3 of F out, right? And then we see what? A and point A equivalent to that is point D, so that should be also 1/3 of F out. So you see, by figuring out all our forces on the upper jaw in terms of this unknown F out, then we are able to figure out what's happening in the lower jaw. So now we are pretty much done. Let's draw the free body diagram of the upper handle or lower handle. Doesn't make any difference whatsoever. So I'll go with the upper handle. So let's try to draw the free body diagram of, okay, we'll do a better job than that. As best as I can do. So look, guys, you have a 240 Newton coming from the handle. It's a force that your hand will apply that. So let's see. On the upper handle, we're going to see point A here, point C here, and then point E. Let me label them A, C, and E, right? So one thing you have to understand when you're analyzing machine problems or frame problems, which are usually together in one chapter in a typical statics book, is that you see how the force at point A, AY is 1/3 of F out here, right? That is the force that the handle exerts on the upper jaw at that point on point A. Now, the force that the upper jaw exerts on the handle would be in the opposite direction. So you see that 1/3 that is pointing up, 1/3 F out, is going to be down. Action reaction, basically the third law of Newton's. All right, what about C? C is just a pin. You know that Cx is going to be 0, so just don't worry about it because we're going to take a moment about C. Now, the other thing is point E here, and that's why we needed the information for the lower jaw as well, because that upper handle is going to hit the upper jaw and lower jaw. So this was point E. Look, the 4/3 F out that is pointing up is going to be pointing down here. So in the opposite direction, action, reaction. So you see now, guys, the only unknown I have here besides Cx and Cy, of course, is F out, which I can solve for by simply taking moment about C. All right. So if I do that, let's see, counterclockwise positive. Let me start with this one, 4/3 of F out. It's going to go which way? negative clockwise about C. What's the distance between E and C? 15 millimeters, as you can see those dimensions, right? Make this so it resembles a 5 here. Oops. Yes. I rewrite this as 1, 5 here. That's 15 millimeters. Then what's the moment of this 1/3 F out at acting at E, at A? So also the distance between A and C is 15 millimeters, as you can see. And that is going counterclockwise, actually. So 1/3 F out times what? Times also 15. And then finally, the applied load, 240, the moment of that going counterclockwise, positive. So this was actually positive, sorry. Plus 240 times what? What's the distance between the 240 and C? Let's see, 90 here and a 15 here. That's 105. So when we clean this up, it looks like we get, let's see, 40, 60 minus 15. You see, we have minus 60 over 3F out plus 15 over 3F out. That guy goes to the other side, becomes minus 240 times 105. It's just a simple math here, guys. So minus 20 plus 5 becomes minus 15 F out. That negative obviously is going to cancel. So look, guys, F out becomes what? 240 times 105 divided by 15. And that's a very good and effective pliers, because you see 240 times, basically the ratio that you're looking for is this. This is an input force, right? And that ratio becomes 7. So actually your output force is going to be 7 times 240, which is 1680. See? Very effective pliers. In other words, the ratio of, if you call this input force, the ratio of output to input came out to be what? 7, because you ended up getting what? 1680 and your input was 240. That ratio is important. So if you apply 1 Newton here, you get 7 Newton here, 7 times. So that's a very good pliers. Okay, thank you as always by watching and listening. I appreciate if you like the video and subscribe to my channel. Thank you, and I'll be back soon with new videos on different topics, subjects. Thanks again.